everybody. In this talk, I would like to tell you a bit more about the recommender systems, what they are, why they are useful, and specifically how to use deep learning in recommender systems. At first, I would like to talk organizers for inviting me. So let's start. My name is Jakub Mačina. I'm machine learning engineer at Exponea, and I'm also teaching assistant and research lab member at Slovak University of Technology. And I love open source software, so I'm a contributor. So the agenda for today is, at first I would like to tell you a bit more about the motivation, why we need recommender systems at all, what are the traditional approaches to recommender systems, what are deep learning, how can you use deep learning for solving recommendation tasks, and then I will present you one case study we did at my company, at our company for fashion e-commerce. So we are living in the era of information overload. There are more than 400 hours of videos uploaded every minute. There are more than 50 million songs available at Spotify. Do you know which one is the best for you to watch or listen to? Do you know which one to listen? It's very hard. It's too many information, too much data. So what we need is some kind of recommender systems. Something that will present to us the most relevant information to us, what we will like the most, or what we enjoy the most. And as you can see nowadays, the recommender systems or recommendations are everywhere, from Netflix, Spotify, LinkedIn. And the core of many businesses is in the recommender systems. But what is the goal of such a system? Usually, in more general or broad overview, is to help customers or any user find content to maximize their satisfaction and retention. So, as I see it, it is to help people to find the content they enjoy and to make them happier by enjoying this content. And what is the value? For example, for Netflix, 80% of hours streamed at Netflix come from recommendations. So it's a lot. For e-commerce domain, like Amazon, 35% of product purchases come from recommendations. And at the scale of Amazon, it's quite a lot of money. And as you can see on this screen, nowadays, everything is recommendations. Like whole web page is dynamically created personally for you. You could see that there are multiple rows, and within the rows we have a ranked list of products sorted from the most relevant to least relevant. So what we care about in the recommender system domain is the first, say, 10, 20 products which will be shown actually to the user. So we compute metrics such as recall adds 20. And what we also typically do is to use ranking metrics, such as these two listed there, because the ranking is the most relevant thing. So if the most relevant item is not on the top of the list, we penalize the algorithm. And what we are doing at Exponea, basically, it's a customer data platform, which is much more broader term, and it's business-to-business company. So we are collecting data about customers, and these customers could be analyzed, and their behavior could be analyzed. But one part of this system is basically recommend a system as a service. So our clients are other e-commerce businesses, and we provide them recommend a system. And these recommended systems could be created easily by, for example, marketing people, and could be deployed to the emails or to the website. So what's the challenging here is that the data are various quality, and they are very diverse. For example, we have fashion clients, but we have also clients from travel and so on. And it's currently for 100+ e-commerce businesses. And when we will talk about e-commerce, this is the typical flow the customer will follow in e-commerce business, like in any e-commerce business, like selling, for example, fashion. Majority of the customer have just seen some items, viewed them, seen the detail, but only small fraction actually add something to the cart, and also small fraction from this actually buys something. So these are the data we're working with: purchases, views, set to cart, and so on. And we have also access to the product metadata, product catalog, like price of the product, image, and description. So these were the data. So what are the traditional approaches to the recommended systems task? So at first, as I mentioned, the goal is to provide suggestions to users for items they maximize their satisfaction. So usually what we have is we have a set of users, then set of items, and interactions between these users and items. Typically, in the recommended systems domain, we view it as a matrix, users times items, and the interactions are there. So if there is one, there was some interaction, and if there is zero, there was no interaction at all. And the task is then estimate the utility function that automatically predicts how user will like an item, or what are the top and let's say top 20 products for a customer. Okay, and what are the challenges there? The matrix is extremely large. As you can see in typical e-commerce business, less than or more than 99% of values are zeros, so it's very large and sparse. And there is a well-known problem of cold start. What is it? It's the answering the question what to do when we have new user, which we don't have any data about, or new product, which we have only just metadata, for example. So these are the challenges. And what's the basic approach how to solve this is called collaborative filtering. And basically, what it does, it finds the most similar users to you based on your common interaction with the other user, and recommends you the item the other person like or enjoyed, but you haven't. So very simple idea. But what's next approach, very popular one, is called metrics factorization. And the idea of this approach is to basically factorize this big matrix into two small matrices, where the dimensionality of this k is small, let's say 100. So we will, and then we will work with these smaller matrices. The idea, like the general idea, is to go from big dimensionality to small dimensionality to get some generalization, let's say. Okay, and then we can say that how to compute this value, or we can work with this user vector. This is some compressed representation of a customer now, and this is some representation of a product or item. And how to compute this missing value, or how to estimate this value, is just a dot product between this vector and this vector. So this is the idea. And how to compute these smaller matrices, we can see it as an optimization problem, where we are trying to minimize this loss function, which is just the least square of the real rating or interactions minus our prediction plus regularization. So that's the idea, and we could solve it using, for example, SGD, stochastic gradient descent. Okay, these were the traditional approaches, and how can we use deep learning? Because we're here at the Deep Learning Meetup. So there are different framings with deep learning for recommended systems. We could see it as a metrics factorization extension, so something similar. For example, to predict the interaction not just by dot product, but by neural network. Or we could use autoencoder to encode or compress the information into some smaller vector. meta approaches. See it as a task similar to what Veg is doing. Or there is another family of approaches which is next event predictions. So we see this problem as a sequence predictions that this customer viewed product 1, product 2, and what will be the third product, what will be the prediction for the third product. Or the last family of approaches is to just use the content of the products. For example, to use convolutional neural network to process images of the products and find similar products. So, for the first approach, what we would like to do is the same task as in the matrix factorization. So we have some user, some item, and the prediction is interaction. But instead of the dot product, which was in the slides before, we use deep neural network for prediction. And by using this, we have like more computing, like more power, or we can model also non-linear here. So that's the advantage. But as was shown here by Netflix, the gain compared matrix factorization to this approach is very, very small. And it's not big benefit, so it doesn't help us a lot, like when you compare also the computing power and so on. So what does it mean, like what to do now? However, deep learning is very useful when we are adding additional metadata about the products to recommendations. So in this paper by YouTube, by Google, they are kind of state of the art approach now for the recommender systems task. So they use two steps approach, and that's at the first step they use retrieval, and then they rank it. So they come from 1 million of products to 100, and then they rank just these 100 items with much more rich features, for example, extracted from the videos. So let's dig deeper into both of these parts. So for the first part, for the retrieval part, what they are basically doing is on the input there are your past video watches, what you searched, and they are represented as embeddings, and there are some metadata about a customer or a user, like gender or age. And then there are layers of neural networks, real layers, and the prediction is the distribution, whether you will like what video you will like the most, or what are the distribution of the videos you will like. So that's the idea of the first retrieval part. And what's very interesting about this approach and in the era of deep learning is that we could represent users and the movies as an embeddings. Maybe I think you know about embeddings, but it's a like compressed representation or latent representation of user and movie. So, and in this particular case, the user embedding is represented as the last ReLU layer in that deep learning network. And the movie embeddings are the weights connecting the last ReLU layer with the softmax function, output. Yeah. So that's the idea. And for the second part, for the ranking, so we come from millions of videos to just 100. And for this task, we could use much more rich metadata. For example, we could use everything what we know about the video and about the user, and represent it as an input, and then predict different metrics. For example, what YouTube was doing in 2016, they were predicting in this second step, ranking part, they were predicting watch time. Like for this particular video, how many seconds or minutes will you watch? So it's completely different tasks. So they separated these recommendations tasks into these two steps: first ranking and the second, first retrieval and the second ranking. Okay. And then another approach for recommendations is to view it as a sequence. So this is my sequence of what I view at some e-commerce e-shop. So the first product, second product, third product, and what will be the prediction, my next predictions for this next item I will launch. And when you just think about it, it's great for recurrent neural networks, and because you could use this information about the time dependencies, like what was the first and what was the second. So this was the idea of this paper, and they use basically gated recurrent units for modeling this task, and they basically predict next item in a session, and they get some improvement by modeling these temporal dependencies. Or it could be, in the real world, it's more complicated because users have sessions. So they in this paper, they've used one recurrent neural networks for modeling sessions, and then they reuse the hidden state of this recurrent neural network to model like long-term preferences of a customer, of a user. And then these long-term dependencies are an input for this session neural network, which models short-term preferences. Okay, so recurrent neural networks. And here in this part, I would like to present you a more detailed approach, what we did for one fashion e-commerce client. So these were our settings. It was fashion domain. It was one particular website, and the challenges in the fashion domains or in this website were the intents of the customers are changing very rapidly. Also, the trends in fashion are changing very rapidly. And also, most of the customers visit site just a few times a year, so it's not a lot of data to work with. And the metadata about product catalogs were usually in the poor quality, missing categories, and so on. And we tried to build this quite general terms. And also, customer rarely buys the same product twice. So these were the challenges. And what how we try to address them is we decided to not use metrics factorization because it takes into account your whole history, your every interaction you did. But we try to prefer more real-time adaptable approach, and also prefer latest information from session, for example, and prefer behavioral data. I mean behavioral data, your interaction. And what we did is, our solution was session personalization by port-to-wake, and I will explain what I mean by this. The idea here is called like co-occurrence modeling. So we suppose that each customer, when it comes to this website, has an intent. For example, I would like to buy or view formal business shirts. And this is his current session. So I would like to know what other customers in this intent viewed next or seen next. And when you think about it, it's very similar to what the port-to-wake is doing for words. In this approach, for example, the word bank could be used in the context of when we talk about the banking sector, ATMs and so on. But also, bank refers to like a riverside. So these are two different contexts. So why not inspire from the NLP domain and from the success of port-to-wake? So just very briefly, for you, what is port-to-wake? I think most of you are aware of what it is. But it's basically it's an unsupervised learning approach which represents each word as a very dense numerical vector, usually like tens or hundreds of size, and it represents words which are very similar or used in similar contexts with embeddings which are much more similar than the other words, for example. And what it basically is, it is a feed-forward neural network, and the task of word-to-vec for words, it analyzes all of the corpuses and documents. It predicts, or it tries to maximize the log likelihood of your surrounding words given some target word. And this log likelihood is estimated as a softmax function. So this is the idea, very famous by Niccolo word-to-vec. So let's see how could be this applied to record systems. So the general idea is to have your current session or current session of customer somehow represented as some small vector. And then we could easily find similarity to each other product in our product catalog just by, for example, cosine similarity. This is the idea. And which data to use for training such a model, or how can we model this? Our training data were like past sessions of customers. For example, this customer viewed these 3 products with these product IDs. Then the second customer comes, we viewed these 4 products with these IDs, and so on, ordered in time. And when we say session, we mean like the session ends after 30 minutes of inactivity. So we use these IDs of products, just these IDs, and use skip-gram model, which is proposed by Niccolo in this word-to-vec paper. And when going from t minus 2 to t minus 1, t and t plus 2, this is one example of training data. So this is how we model it. So on the input is just one product, central product, and we are trying to predict what are the other products viewed in this session. So this is the task, and here are hidden layers. And at each step, we would like to use neighbors as these real neighbors as the positives, and some random other random products as negatives. So that's the idea, and just to give you some intuition, how it's working, there is a sliding window of 2, and if this is the session, then we would like to have these products come together. And we would like to pick one random product and push these relevant products away from them, like this. And then we move our sliding window, and then again push products which were in this session together. And like this, we have all of our products in the space where the relevant products viewed in similar patterns are closer in space than the other products. And then what we could do is it's very easy. Just when we have, like, for example, 100 vectors like this for each product, we could very easily compute the similarity. So, for example, the similarity between these 2 products is this number. And then what we could do, very important for fashion, we could analyze and understand the clusters which the model trained. So here you can see after applying the PCA in the third 3 dimensions, so we see some clusters of trousers here, and other clusters of bags here. Or we could colorize it by categories. So here are some categories from the product catalog. So we could see some category here, some is there. So at first we could get an idea if it's working fine, and then we could also analyze it. And this is one example of what we could discover in this space. We could, for example, discover that the first, after applying PCA, that the first most important component is men versus women. So it's just some kind of gender. And the second, for example, kind of component is formality and casualty. So some products, this is the groupings which we discovered. And this product space is very great for retrieval and finding similarities, and it's very great for scalable architecture and for real-time personalization. So we could easily have like 1 million products represented in such space, and could do operations when we have a customer which viewed just this one yellow dot. We recommend him the nearest products in this space, very easy by customer similarity or any kind of similarity. So here are the results. For this dress, we recommend these dresses. For these shoes, other shoes or similar style. And I would like to remind you that we just learned this based on the sequence of customer actions. So there were no images or textual descriptions in the training data. So that's the idea. And yeah, for another dress, something similar or alternatives. Yeah. But we could also represent the customer very easily there. So if the customer views these 3 products, green, red, and yellow, we could put the customer in the same space just by some weighted average, and then we could recommend based on this, recommend him the products in a similar style to what he's currently watching, for example. So it's working quite well. And even more important in fashion, we could find dimensions in the space. For example, when we subtract these 2 products, we know that this dimension is formal dimension. So then anybody could add to customer vector this dimensionality, and we could recommend to the customer still similar, relevant items, but much more formal one. So this is a quite good advantage of modeling it like this. So we have the dimensionality. And what we find out how to tune it to be even better. So the most important thing for us was the quality of data. So we, for example, filter out short clicks, and we also tries to have an open feedback loop. What I mean by there, that the data, if only our recommender was on the website, the data will be passed by the recommender which was deployed previously when we collected our data. So we will try to have other means by how customer could find the products. So that's what I mean by open feedback loop. The other approach is to not do, or what work quite good is to not pick random products, just by random, but to, as a negative samples, use products, for example, from the same category to make it for the model much harder to train. Or even better, you could model this as a customer who viewed this, then bought. So there we have sessions which ends with purchase. There are only some of the sessions which ends with purchase. But when we know that this session ends with purchase, we could, in every training example relevant to this session, we could include the purchased product into the training data as a positive. So this could be even improved like this. And yeah, when we this is from the paper, but when we compare it, it has like slightly better results than the just metric spectralization form. Okay, so just some conclusions from this talk. As you've seen, the recommended systems or recommended engines are instruments of your or every e-commerce business. So most of the value, for example, from Netflix or Spotify, come from the recommender systems. There are a lot of applications and open research questions. So it's still quite a research area. And where the deep learning helps is only when we add additional metadata. For example, images of the products, textual descriptions, or video embeddings, and so on. So that's important for, I think, this community. And as you've seen, Vortibek is actually a recommended engine. which could be used, which has good properties, scalability, and it has good property like the dimension in that space, which you could use, for example, in fashion. It could be used quite good. And with this, I would like to start the discussion, and there are also my colleagues from Exponea, so talk to us or visit us in Bratislava office. And yeah, thank you very much, and looking forward to the discussion.
Thank you very much, Jakub. Thanks for this excellent talk, going very much into detail.